All right. So we have this idea, and by the way, what I'm talking about right now is all Kepler laws, orbital mechanics. So I'm calling it the first law of orbital motion, but it's Kepler's first law, actually. Okay. So we have this first law of orbital motion, and the law looks like this. If I have a string, if you like, that connects A, B, and C to form a triangle, I could take my finger, just like I'm taking the tip of my pen right now, and I could slide it along the ellipse. What that means is, and I'll do it with a different color, if I put C primed over here, there would be a new triangle that would be formed. It would go like this. You see what I mean? Now, if my pen's over here right now, the perimeter of that triangle when I'm at C primed, according to Kepler, is the same perimeter as the perimeter of the triangle when I'm at C. That's kind of a neat property. Now, you can test this. The nice thing about this is it doesn't require a computer or a calculator to test it. And the way that you can test it, and I'll pull out a piece of string later if you want, I grab a piece of string and I tie it together at both ends. And I have a student put their finger, two fingers down, one finger at position A, one finger at position B. And then I take another student and they put a marker at position C and they just slide. You guys ever played with like a spirograph or something like that? This is kind of like spirograph. You slide it around, and every single time, if I keep the string tight as I go, it'll trace out a perfect ellipse every single time. So the proof is an activity, actually, if you want to do it that way. We don't even need to do any calculations for it. But what this means is, the impressive thing really is that he observed it from Earth. He didn't get to zoom out to above the solar system to see this somehow. He observed it based on what he was seeing where the planets were in their orbital paths around the Earth. That's the impressive part to me, really. But these 2 points here are called the focal points. And these 2 focal points, well, one of them is where the central body would have to be for the elliptical orbital system. So maybe the sun is at position B and the Earth goes around. There's nothing at position A. It's a geometric artifact, okay? But there's nothing at position A. So if you're somebody who's like, oh, well, Nibiru, isn't that the mystery planet? There must be some mystery planet at the other focal point. It's always like these online, isn't that the thing? The online conspiracy theory, isn't that the name of the other planet? I'm getting the wrong activity feeds. My goodness. This is the problem. You click on a few of these things from the Flat Earth Society and they send you all these things. But the other neat thing about ellipses is that ellipses come from a family of shapes called the conic shapes. And if you slice a cone diagonally, you're going to get an ellipse. The other neat thing is that this focal point is actually a literal focal point. If you remember in optics in grade 10, if you have a conic shaped mirror at either end of a tunnel, and you put a candle at the focal point of that conic shaped mirror, that concave mirror, then the light will go out in all directions, and the reflected light travels parallel to the principal axis, and then will focus back at the other focal point. This is a really neat thing. Now, I happen to have, and by the way, this also works for telecommunications. Can you imagine that these aren't just mirrors, they could be satellite dishes? And this isn't just a candle, this is a radio signal point. And so there's a radio receiver here and a radio transmitter here. Like this idea of conic sections and the idea of focal points is a powerful thing. When I was a kid, not much older, no, not older, around your age actually, I taught English in the Czech Republic. I had a friend whose parents were from the Czech Republic. They left when communism was falling, and they actually escaped inside of the engine blocks of cars. So like an exciting story there and everything. But when I went back to teach English there with my friend, we got to go to Prague Castle, and there was a benefit that was happening at Prague Castle at the time. And in this ballroom, there was this place where you could stand in these 2 particular places in the ballroom, and you could whisper. And my friend's grandmother insisted that we do it. You stand at this one place, and there was a marking on the floor. You could identify the place. I don't know how many people know about this thing, but you could stand in this marking on the floor, and the girl, my friend, she could stand at the other spot, and we could whisper to each other. It was a crowded room, right? Like there was a fundraiser going on. The Danube River had overflowed, so people had gotten flooded out. And so this was a fundraiser where tons of people were coming to see classical music in the castle. Lots of people were in the room. And we whispered to each other from, let's just say, either end of what seemed like the size of a gymnasium, because of this whole thing being a very real focal point transmission system. You know, The imagination wonders, why did they design a room that way? Were there people trying to have romantic hookups in the middle of royal events or something like that? I don't know. Or was it just cool? By the way, Kepler's lab was just down the street within the castle. So this is kind of just like a neat side note about that. I think it was really neat. Anyway, telecommunications or secret meetups at the ballroom in the castle. Who knows? Moving on down, though, I want to do a little bit of fill in the blanks. And you can hear my voice going. But earlier, I said that the area swept out by the line connecting the orbital body to the focus. I don't think I used the word focus yet. I just said the central body. For a given time interval, it's going to be equal. And I've got an illustration here. I've done my best to sketch this out. Truthfully, I think that this shows better as an animation. And so I do have some animations linked on the website. I can't animate my paper, sadly. The idea is that when your body is near the central body, when your orbiting body is near the central body, you're going to go fast, fast, fast. And as we said before, because of conservation of energy, when you're far away from the central body, your orbiting mass is going to go slow, slow, slow. So if you think of each of these lines radiating out from the central mass at one of the foci as being almost like a minute hand on a clock, tick, 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 tick. Each one of the ticks would represent an equal interval of time. And what Kepler says for his second law is that for each equal interval of time, each tick of the hand, if you like, as it goes around the clock face, and I get that this is a weird clock face, it's an elliptical clock face. You couldn't really do this with a mechanical clock. You'd have to have like some sort of digital clock that like animates this. But the tip of the hand of that clock would be slower out here, and the tip of the hand of the clock would be faster up here, and the areas would be equal to each other. Now, again, the impressive thing to me about this is that Kepler observed this from an Earth-based observatory. That's amazing. I want to give credit to people that do amazing things. Cavendish and Kepler. Fantastic. Now, both of those people very well funded. Cavendish had his lab in a fancy barn in his backyard. He was one of the Dukes of Devonshire. Kepler was funded by Prague royalty. You know, money helps, right? So when we're out here, far from the central mass, slow. When we're close to the central mass, fast. I think I might have misspoke in an earlier video. So there's the correction on that one, okay? And so people talk about faster arc speed when you're closer to the center. And sometimes people, when they're thinking about arc speed, they're not talking about the speed around the curvature. They're talking about the change in theta, the angle, as a function of time. So rate of change of theta is actually bigger as well. If you measure theta as between those two hands on the clock. We're not going to do that math just now, but that's another way to think about this. What we're going to consider, though, is stable orbits for circular pathways. Mostly because we don't have the math skill set to deal with elliptical pathways. You probably would guess that most orbits are more eccentric. Most orbits are not circular. That just seems to reason that most things aren't going to have just the right speed to travel around a circular path. Most objects that are captured by a gravity well are going to have kind of lopsided orbits. But for our purposes for high school, we're going to deal in circular orbits. And so I want to do a little bit of a cheat right now, and I want to use Post-it notes to break this up. I want to say that if I'm in a circular orbit, I recognize that the force due to gravity is going to be equal to the centripetal force that body experiences. I think on a recent evaluation, there was some question about whether the orbital speed was mass independent or not. Notice, mass cancels out for an orbital body. So the speed at any given time for this orbital body is not dependent on its mass if it's circular like this. I bet you there's a connection to mass if I have to have this interplay of increasing and decreasing gravitational potential energy and kinetic energy. I bet you we can't quite do that, but maybe we can. Turns out the gravitational potential energy also has the mass of the orbiting body in it. So does kinetic energy. But we get the V all by itself. I'm going to call that equation 1. And M in this case is the central body, not the orbiting body. It's the body, like, for example, if Earth was going around the sun, Earth was the mass that just got canceled out. The central body would be the mass of the sun. Now, something else that we know is that when you go around a circle, speed is equal to 2 pi r over the period. That's kind of like saying speed is equal to distance over time, except 2 pi r is the circumference of a circle, and the period is how long it takes for a repeating event to happen. And an orbit is a repeating event, so it makes sense to talk about it in terms of period. So there's an analogy there to distance over time. I got to check the room because it's hard when I'm not being the writer to gauge how fast people are doing things. And that's why I don't use slides very often. I like to pace myself with you guys. How's the pacing? Are you guys keeping up okay? Some people say yes, some people say struggle. Okay. Does this make sense so far, though, for people? I would say what we're doing right now is more mathy. The other stuff is more geometry-ish, right? More shapes. But it's math that we've seen before. So I want to look at that idea of 2 pi r. And it looks like if I have an expression for v and I have an expression for v, I can mash these things together. And I would end up getting an expression for period in terms of 2 pi r and the square root of gm over r. Notice that what I've done here is, with the equation I'm pointing at right now, I've just cross-multiplied period and speed, and then subbed in equation 1 for the speed value. That's what we're getting here in this line at the top. Okay, so just so it doesn't seem too mathematical, that's what just happened, okay? If we want to see the steps, these are the steps. Cross-multiply the period and the speed, sub equation 1 into equation 2. Now, if I want to make things a little bit simpler to deal with, it seems to me that we should square both sides, just to get rid of that square root in the bottom, because that's ugly. And what you end up getting is period squared equals 4 pi squared r squared over gm over r. Of course, we got to invert and multiply that denominator to get period squared equals 4 pi squared r squared times r over gm. That makes things a little bit neater because that r squared times r becomes an r cubed. I'm not even saying it's beautiful, but it's a little bit neater. Now, something I notice, 4 is just a number. Pi is a constant in the universe. G is a constant in the universe. And Kepler was limited to just looking at our solar system, not every solar system everywhere. I mean, for goodness sake, he was limited to our planet, and he did a pretty good job of looking at our entire solar system to, the eye that could see what planets were there at the time. So that M was the sun. So that was a constant for all the planets in our solar system. It's the central mass for all of the orbiting bodies in our solar system. So what this means is that if I can isolate to get period squared over r cubed, 4 pi squared over gm, that 4 pi squared over gm is going to be a constant for an orbital system. Doesn't matter what body's orbiting around it. Doesn't matter what planet is orbiting around the sun. Our solar system has that as a constant. And Kepler called it his Kepler constant. It was the Kepler constant for our solar system. Every satellite system, though, has its own Kepler constant. The orbital constant, the Kepler constant for our planet, when we have man-made satellites going around our planet, will be defined by the mass of our planet in the denominator there, right? All the other things are constants of the universe. But the mass of the planet, that's going to be a constant for all the man-made satellites orbiting around our planet. Whether it's, I don't know, something from Elon Musk or something from NASA, it doesn't even matter. Now, what Kepler actually did was he left it like this. The constant for a satellite is equal to, he inverted both sides, is equal to gm divided by 4 pi squared, which, as we can see, is equal to r cubed over period squared. M is the system's central mass, and all of the planets in our solar system which share the same Kepler constant. In other words, if you knew the orbital radius for Neptune, then you could calculate how many days long its period is. That's a relationship. And Kepler did it. So we'll make sure that we have enough time for everybody to write things down. I have a few info boxes off to the side there. So if you're into like historical facts and things, you can definitely go and read those. But I'll leave everything up on the screen. And I'll pause the recording.